Have you ever stopped to think about math as a language? I mean, really think about it. It has an alphabet, it has grammar, it has sentences, just like any language you and I speak. But here's the kicker. Its rules are so incredibly strict, so precise, that they let us build entire universes out of pure logic. And it's this language that helps us explore the very edge of what we can possibly know. So, to take us on this little journey, we're going to be using the incredible work of mathematician Manin as our guide. We're diving into his book, A Course in Mathematical Logic for Mathematicians, to help us decode this whole secret language. Manin kicks things off with this amazing quote. Self-caricature. What on earth does he mean by that? Well, he's saying that when we formalize math, we're kind of creating a simplified, almost exaggerated version of it. One where the most important parts of mathematical thinking just glare out at us, plain as day. And it's that caricature that lets us actually study mathematics itself. All right, so to get a handle on this language, we've got to start with its grammar. In the world of logic, we call this syntax. Think of this as the first layer we're peeling back, the absolute foundation of the whole system. Now, the most important part of this slide, the part that's kind of wild, is right at the end, without any regard for their meaning. Syntax is totally mechanical. It's just a set of rules. It's like chess, right? The rules tell you a bishop moves diagonally. The rules don't care why or what a bishop means. It's all just about which moves are legal and which ones aren't. And this shows you exactly how it works. You start with this teeny tiny alphabet, just a few symbols. Then the syntax rules tell you how you're allowed to stick them together. First, you make terms, which are kind of like the nouns in our language, something like x plus 1. Then you use those terms to build formulas, which are like the complete sentences. X plus 1 equals y. Every single valid statement in math is built up just like this, piece by piece, following these super strict rules. Okay, so we've got these perfectly built sentences, but right now they're just meaningless strings of symbols. They don't mean anything. The next layer we have to peel back is semantics. And this is where the magic really happens. This is where we finally connect all those symbols to an actual mathematical world. So this is the really crucial difference right here. Syntax is the rulebook for building things. Semantics, that's the dictionary that translates what you built into statements about something real, like numbers or shapes or sets. So to put it simply, syntax is all about structure. Semantics is all about truth. And this whole process of giving symbols meaning is called an interpretation. For instance, we can decide to interpret our symbols to be about the natural numbers, 1, 2, 3, and so on. In that world, the symbol for a plus sign actually means addition. Or we could interpret those exact same symbols to be about the universe of all sets, where a symbol might mean one set is an element of another. See? Same grammar, totally different realities. So you might be thinking, okay, why go through all this trouble? Well, because once you have this entire system set up, you can take complex, sometimes kind of fuzzy human ideas and translate them into a perfectly precise, totally unambiguous code. Let's take a really simple, intuitive idea from set theory. We all kind of know what it means for one set to be a subset of another, right? It just means that every single thing in the first set is also inside the second set. Pretty straightforward. And here is that exact same idea in formal language. Now, I know it might look like a random jumble of symbols, but don't worry, let's just quickly walk through it. That first symbol, the upside down A, just means for all. So for all y, then we have y is an element of z. That little arrow means implies. So the whole sentence basically reads, for anything called y, if y is in set z, that implies y is also in set x. Now, the point isn't for you to become fluent in this stuff overnight. The point is to see how this string of symbols captures that idea of a subset with absolute perfect precision. There is zero ambiguity here, no room for error. It's a perfect translation. So what? We can write math ideas in a weird-looking code. Why is this such a big deal? Why is this considered one of the most profound achievements of the 20th century? I mean, what does formalizing math actually let us do? Well, this is why it all matters. This whole way of thinking is the bedrock of computer science. Every programming language you've ever heard of is a formal language with its own strict syntax and semantics. It's literally how we give computers instructions without any confusion. But it goes so much deeper than that. By treating math as a language, we can actually study the language itself. We can start asking crazy questions like, are there true statements out there that we can never, ever prove? And spoiler alert, the answer is yes. That's Gödel's incompleteness theorem. This lets us ask the biggest questions there are about truth and proof. And all of that leaves us with this one last, absolutely fascinating question to chew on. We've built this incredibly powerful, super precise language. But here's the thing, every language has its limits. So by defining so clearly what mathematics can say, we've also, maybe accidentally, opened the door to asking the most profound question of all. What are the things it can never say?